So now, once manganese produces oxygen, then oxygen changes everything. And oxygen changes everything through redox potentials. That's why I don't produce this, but it's kind of interesting. Redox potentials don't become important until about halfway through Earth's history. So we've been sort of tracing Earth's history through the book. And it's something that I didn't really intend, but it so turns out that Atkins puts redox chemistry at chapter 5, which is the same place in the quarter at which we get to the chapters 7 through 9 in this book. Let's see. So realize this, manganese is allowing stuff to be captured. It's basically producing, photosynthesis produces sugars and oxygen, and the key is those are chemically unstable relative to CO2, relative to H2O. Once light is captured, the delta G of the products is actually higher. This is a delta G that's positive. It all works out because the light is driving the reaction. Once you have these in the environment, sugars and oxygen, then you can take the two things and you can put them back together. And then you get the negative delta G, and then you have energy, and then you have kids at a birthday party who eat a bunch of cake and they have a sugar rush because they're breathing oxygen, they're eating sugar, and they have a lot of energy from that. That energy ultimately comes from the sun. And so this is one of the ways that the Earth isn't dead. It isn't just a low decay, like an exponential decay, because you have other reactions going on. You have an exponential going up thanks to light. So the sun is what's really powering that. In a sense, it's like the roller coaster hill. You know, on a roller coaster, if you don't have one of the launch ones, you have a big hill that you go up. The sun, in a sense, is doing that to free energy. When you're at the top of the hill, you have sugar and oxygen. As you put them back together, you have the roller coaster ride, the sugar rush. And as that happens, heat is actually given out. Realize that the second law of thermodynamics is still being followed because high energy light is coming in, low entropy light is coming in, and high entropy energy, like heat, sunlight is actually going out because it's being reflected and it's stretched out. So it's also dispersed. It's also higher in entropy. So the whole system works because on the whole, it actually does expand entropy. And so if you look at the life before and after photosynthesis developed, you expect to see some differences, and you see differences at pretty much every level, including the level of color. This is at the San Francisco Exploratorium. And they have this thing where I guess it's like an ant farm for microbes, because they have two big slabs of glass, and they show you that they have microbes growing in it. It's a little bit like the tube that I brought to class, but that was just on redox chemistry of rocks. This includes microbes, but the microbes also, they have similar colors. And if you look before oxygen, you have purple sulfur bacteria. The purple sulfur works in a low oxygen environment, and it actually reflects the kind of light that you're capturing, and it reflects the energy that you're using it for is not the energy that you need for photosynthesis, so it's less energy captured means a different color. So purple means low color, and after oxygen you see more red and green. You know, for one reason you see more red is because you see more iron 3, and that makes rusty red color. But the reason you see more green, that is manganese green that captures the center of the light from the sun. And it will actually have enough power eventually to drive oxygen production through photosynthesis. So this red and green, you can possibly tell just by looking at the different sides. And that's their whole point here. They say oxygen changed the world. So the Exploratorium is saying it too. This graph is how it shows, and this is one of the central graphs in the book. If you want to imagine it in color, you can imagine this being a big orange thing, and you can imagine this being a green arrow, because the green of photosynthesis goes with manganese chlorophyll molecules, and the red rusty molecules that precipitate out, those are going away from life into the solid phase. The green is part of life. And so you have all the nice green that we can see out the window, and hopefully at 12 o'clock you can enjoy it, except for Rosemary, who's going to be in the lab. But oxygen, notice that oxygen is going up, and oxygen is going up in 2 steps, and it definitely changes chemistry because you see banded iron formations associated with the increase in oxygen. It all fits together. Realize that as oxygen goes up, oxygen has a certain high redox potential. And so this redox potential is way up here. As oxygen increases in concentration, the redox potential of the whole Earth goes up. And that's a literal thing to say. Remember that redox just has to do with how electrons are moving. It doesn't really care, but you can put anything in as an electron source and electron destination. You really care about how the electrons are moving. Which direction do the electrons want to move if you put something out in the air? And what this is saying is that these different redox potentials, as the Earth moved up in redox potential, you change the form from the form on the left side to the form on the right side. And you can see that just from the redox potentials, and these are very crude. I want to say that this doesn't exactly predict step by step what's going to happen, not because it's wrong, but because the system is more complex. But it's just amazing that information you can get from a lab using electrodes, just on these basic things at pH 7, that it still roughly correlates with what happens in the complex and dynamic and evolving Earth at all. That means that the lab knowledge is actually true knowledge in some way. And so the redox potentials can predict that, for example, vanadium would change to its higher oxidation form fairly late. And one of the first things to change would be sulfur changing from sulfide to sulfate. And you would have molybdenum also being connected to this. So you have these different things hanging on. We get an approximate sequence from this, that earlier should be mostly on the left side, and later should be mostly on the right. The way that RJP Williams did this, and this is a weird way to do it, and I want you to see it, because this my way of doing it is to make it a straight line and an arrow, because time is a straight line. His way of doing it, for some reason, was to do the redox potentials in a circle with the metals on the right and the non-metals on the left. So at this, you have the lowest potential. There you have the highest potential. And basically, you see how oxygen is right here. And you see how this actually goes with the other one. We just started with hydrogen right here 4 10 to the 9 years ago. And I sort of follow this arrow. The other graph is of this arrow right here, and it puts both of these on the same graph. Other than that, they're the same graph. So I'm hoping RJP Williams got these numbers right, because I'm basically copying them. But these do show you that over time, ammonium turns into nitrate. Over time on this also, by the way, over time, he makes them go, as you go to the left, is what happens over time. But you see how you're losing hydrogens, you're gaining oxygens in general. You're moving from lower states to higher states in general. And those, by the way, this is actually V plus 4. You have to do that little chemistry trick where you know O is minus 2. So you have to do things like that. Actually, I might have, O is minus 2. That works. Okay. So you get these trends, but you get these from the E values. You get these from the tables in your physical chemistry book. And one of the main things is like methane will react with oxidized things to become CO2. Things will become oxidized, and the things on the bottom should become oxidized first. So that means we don't have to worry about running into a cloud of methane anymore, unless we're in a low oxygen environment where it's been kept away from the atmosphere. The atmosphere will make CO instead of CH. And the biggest thing is iron 2 became more rare. It's a very useful molecule, but it became iron 3, and then it dropped out of solution because iron hydroxide 3 is very insoluble. So you can turn those graphs into a timeline like this, where you can talk about concentrations over time, and realize that this is a crude approximate measure, but it does make certain predictions. Iron goes down, sulfide goes down, sulfate goes up, the version with oxygen. And some things are not redox sensitive, so they shouldn't be changing based on the oxidation of the environment. So you have like sodium and potassium should be about the same. So he made this crude thing, and I don't think he went far enough, but you can still, from this graph, you can at least say, what is this one saying the biggest changes are? Sulfate should return, and actually this predicts that copper comes out late. Now, iron goes away, And that's the thing we see with the banded iron formations. We see where the iron went away to. We see the place where it went. And then CU returns. So this is approximately right, but we actually have some data that maybe the CU piece of this puzzle is not that accurate. Maybe there's something else going on other than redox. Kind of like with this kind of argument, you kind of like, you want to make 10 predictions, and you expect like 1 or 2 of them to be wrong, and then you expect 1 or 2 of them to be ambiguous, but then you want most of them to be right. And that's, when you're dealing with a complex system like the Earth, you do that. So this is the data that I presented in the book, and this is actually the data. I want to show you the actual data. This is a biochemical computational evidence. So this is where they calculated when proteins were born. When proteins using the different metals for catalysis or using the substrates were actually first appear in the genomic record. Okay, and it roughly matches RJP Williams' hypothesis. We can go through proteins that use oxygen, and by the way, they have a weird color scale, but red it means more proteins are born, blue means fewer proteins are born. So more proteins are born with oxygen. When you move, you get more white color. Sulfate, you get more white. You start off with blue and you go up, but sulfide starts off with red and goes down. So that matches. Copper for this one matches the prediction. It starts off low, and it even is one of the latest to show up, according to when proteins bound it and used it. And molybdenum is right behind. Manganese right there, starts off high and goes down. Now, by the way, this is manganese. Remember, manganese can be used before oxygen for catalysis, and this is probably what most of these are. But then also around this time, you still have it red. This is when photosynthesis was born, and you had manganese clusters. After that, you actually don't use manganese anymore because it's already doing its most important job. Cobalt, I take this as being mostly red and then going down. And then zinc doesn't really show a trend, even though it's supposed to show a strong trend. And then nickel goes up, which is not what you would predict from the redox potentials alone. So again, you have, and iron also goes up, which is not what you would predict. So here, if we look at our scorecard, we're kind of in the region that I was talking about. 1 or 2 ambiguous, 1 or 2 wrong, and most of them being green equal signs that fit with what they predicted. This is the kind of thing they predicted. And they even see, it's kind of cool, you can see that the great oxidation event directly preceded the birth of genes that used oxygen. It took a couple 100 million years for them to learn to use the oxygen that was accumulating. And then right after 3.0, you get the big burst of invention. This is the number of genes that are born. This is like the gene birth rate. And we know what oxygen was used for. This is one of the best established stories. We know when cholesterol, and we can see cholesterol in the rocks. That's the other thing. You can see these kind of molecules in the rocks, and you can measure, oh, all of a sudden, right after the great oxidation event, you get banded iron formations, and you get cholesterol in the rocks. And this isn't made by non-living things. This has to be made by life. It also has to be oxidized by a strong oxidizing agent. What's better than oxygen for that? So it sure looks like this, and this is exactly where it comes in if you're into the organic chemistry of exactly why you need oxygen. This is what you need it for, to turn this step into that step. And you can't make the 4-ring structure without O2. And the dates for the genes, see this was the first one that they noticed. And the study that we have there just shows the other thing. But what I really want to have new this year, and this is what I was staying up late last night making for you, you have a new figure that came out about looking at the geology of when trace metals were in the ocean by looking at pyrite samples. Something completely different, not looking at genes at all, not looking at life at all, but just looking at pyrite, because pyrite will include include all of these transition metals, and so let's see how much there were. So it will include, for example, this is molybdenum. Molybdenum is supposed to be strongly associated with the production of oxygen, a more oxidized environment. And you see, if you look at the pyrite samples, by the way, this is normal scatter for geology data. About 2,000 years ago, all of a sudden, it goes up. Right after, pretty soon after. I mean, oxygen's like invented here, so it looks like it took some time for the oxygen to accumulate and other processes to go on. But this is definitely post-great oxidation event, pre-second oxidation event. And so they have a cool thing. It goes up as expected, but as with everything that is from a different source, it has a kind of cool little finding. They noticed that the pyrites were low right before life comes on the stage. Cambrian explosion 600. Right before that, there seems to be a low amount of metals. And remember how there's snowball Earth? There's a lot of stress on the whole Earth system at this point. And it could be that stress, it seems like that stress also includes some kind of oxygen stress, where there was sort of a time when there was the whole ocean may have even been more anoxic. At the very least, it sort of lost these oxidized metals. Okay. So what you have is you have this chart, and this is what they do. And again, I'm going to go through this one by one and say what matches the predictions. And this was put out after RJP Williams died, so it's not like this is the greatest definite prediction, right? So the first thing is to look at this area right here. Now the molybdenum famine is this little spot right here. But if you look at this, this is sort of a little bit earlier, the boring billion, and it looks like there's a famine in multiple things at once. And this doesn't really show up in other records. I'm sort of intrigued by it, but I'm also worried that that could be an artifact. So I want to sort of look past this when I'm looking at this. And we got to remember, this is being incorporated into pyrite. It's a very different thing than looking at genes. So the first thing I'll start off with is what doesn't match. You see a lot of copper all the time, except during this famine when nothing seems to do it. And so that doesn't match predictions. But cobalt, on the other hand, does match predictions. It's red, and then it goes down. Molybdenum and phosphorus, they both go up with a burst of phosphorus in the oceans around the 800 to 400, which is consistent with the idea that snowball Earth caused phosphorus and calcium and all these things to be put into the oceans. And phosphorus, as you know from biochem, phosphorus is very important for all kinds of life, but especially multicellular. Zinc is going up. So here's one where the pyrite fits the prediction, where the genes did not. The genes were ambiguous. And this is one that wasn't in the genes, but selenium. Selenium, we only talked a tiny bit about in biochem because it's so modern and so new, and it's very high on the oxidation scale. And that's exactly where it shows up. It only shows up at the very end of the story. It's kind of like, okay, if you know Star Wars, and the Knights of Ren are alluded to in the sequel trilogy, but they only actually see them at the very end. So they only show up at the very end of the trilogy in this sense, okay? Nickel, it's kind of ambiguous. It's like, it does go down at the right point, but all these things are going down, and it goes back up in the pyrite. So I'm going to put that as ambiguous. Tungsten, also ambiguous. It's kind of interesting to me that it's high later and it's yellow at the present point. This should be going down. And so I'm going to put those as ambiguous. And vanadium, same sort of story where it should be going up, but it's going up when other things are going down. So anyways, but if you look past this weird region, it's down and then it's up. And so that's exactly what we would. There are some metals that are in the pyrite analysis that are not in the gene analysis and vice versa. Oh, and cadmium. This is a problem, and this is even predicted in the book a little bit, that as the Earth continues to go on, but more likely from cadmium pollution, you'll end up with more cadmium there. So basically that's my story. That's why I want to sort of go off on our, I want to discuss with the last half hour of class what you have seen and what you think. So after oxygen, you have new metals. You have more molybdenum that can do its molybdenum things, but you also have manganese in a higher oxidation state and iron in a higher oxidation state, which sometimes can do things as well. There's even some enzymes that manage to use iron 4 in a transient way. That's a really neat trick, but that requires high oxidizing potential to be able to kick it all the way up there. And even notice, by the way, metal ion nickel is in urease. That's a new thing that's unlocked by oxygen being a substrate rather than oxygen affecting the nickel itself. So I'm not going to talk about that. The main thing is redox potential is very useful. You can even talk about the redox potential. Remember how the first slide was about how the Earth's redox potential expanded and became more positive, which is farther down on the E scale. And if you look at the different kinds of organisms, the ones that don't use oxygen, they basically will work in only in low redox, negative redox areas, whereas we work at a 0.8 positive area. And if you look at the in-between ones, they also fit this idea that the environment that's accessible to life expanded its oxidation state, and it kept those, you can see these as sort of living fossils. So you see this definite expansion as you look that up. So could you use an electrode of where the thing likes to grow and measuring the redox potential of the environment as one way of dating what how old the organism is? And the final thing is that he actually uses, this is one of the equations even from the book. So he actually literally puts this in here. And he has a table of E values that talks about as you go through Earth history, you move down the table. And you also have to think about solubility and the initial abundance. You know, things like tungsten are not going to be as abundant because they're so big. So there's a number of things to think about, but it's important that the redox state is something that you have in mind. And I'll have test questions for you to demonstrate this knowledge when you put it together like this. Okay? So all those things are old chemistry and then expanded to allow new chemistry, including manganese-4, which brings us back to the beginning. All right. So that is the discussion. Please stand up and stretch. And